So, hello everybody, my name is Aymeric. I'm a PhD student for the PGA and satellite, and today I'm going to present the cooperative localization of underwater robots with unsynchronized work. So, to begin, more and more today, autonomous underwater vehicles, AUV, are used both for military purpose, for example for the PGA, this is the Bethencourt for my hunting, and also for civilian purpose. This is CGG using it for acoustical measurement underwater. And more, there is a need of swarm of robots for their robustness, their expandability, scalability, and for cooperation. The problem, however, is So the problem is the localization of the robots. This is a problem specific to underwater robots, as on the surface they can use the GPS, but underwater there is no specific infrastructure for localization. They can only use dynamic and acoustical localization. Therefore, the objective of my presentation is to construct an interval-based approach for localizing underwater robots in a moving swarm using sonar communication. My approach is going to be distributive, which means that there is no central intelligence that will know the position of each robot or the clocks of each robot. Here, each robot is responsible only for himself and is going to compute its own position and its own clock. The originality of this paper, of this presentation, is to consider that the displacement of the robot while the sonar wave is moving is superior to the precision of the localization. What does that mean? Is that for a robot 1, when it's going to emit a sonar ping at a time t equal a, in the rest of the presentation we will always consider the emitting time to be called a and the receiving time to be called b, k being the number of the ping. Okay? So when the robot 1 emits the ping number k at time a, it will be received by robot number 2 at time t equal b. Okay? So the distance will actually be between the two robots at different time, okay? And this distance will be equal to c, the velocity of the sound, times b minus a, okay? Moreover, we are going to also consider that the clocks of the robots are unsynchronized. This means that the time a and b are going to be uncertain. We are only going to be able to know intervals around a and b. So the problem is to solve an intertemporal system of equations with uncertain time. The principle will be to cast the linear and nonlinear state equations into a constraint satisfaction problem for which interval propagation is particularly powerful. So let's state our problem. For all robots I in our swarm, we will have the following state equation. F will be the evolution equation, with x being the state of the robot, and u being the entry of the robot. And g is going to be the observation equation, with y being the output of the robot. This is really classical state equation in robotics. The evolution equation will actually be used for dead reckoning, and the observation equation will be used for the GPS and acoustical measurements. We are also going to add a clock function called h, with t being the absolute time and tau being the inner time of the robot. The time is sync he had. Okay. Notice that the observation function depends on the state of the robot at the current time. But in our approach, we're going to consider a sonar communication between the robots, which will lead to intertemporal constraints. So let's rewrite this in an intertemporal form. So 1 will still be the evolution equation. We are just going to add a state noise and x, and consider that the state x is actually the position of the robot. Okay? And g is going to be this intertemporal form, with xi being the position of the robot when emitting the ping at time a, the position xj of the robot j when receiving the ping k at time b and time a and time b. This can be rewritten as the norm of xi minus xj minus c, versus the celerity, times b minus a. Note that this corresponds to the Minkowski norm used in the relativity theory. And we can also write equation 3, constraint 3, where a tilde will be the inner time of robot I, and b tilde being the inner time of robot j, okay, when receiving the ping. And the clock equation h point of a equal to 1 plus a noise nh, okay? We know that this noise is bounded. So we are also going to consider that each ping contains the estimated position box of the emitting robot, along with the interval around the emitting time in the robot's clock. Okay? So the ping is actually enclosing some data. So what this means is that for a robot J receiving a ping k from I, we know what? We know a tilde, the inner time of the robot emitting, the inner time of the robot receiving, b tilde, the emitting robot I, the receiving robot J, and the position of the emitting robot. And what we want is to contract intervals around the real emitting time A and the real receiving time B, and to contract the position around the position of the receiving robot, xj, okay? And actually when contracting A and B, this